Economic and political discussions about hydrogen produced from renewable energy sources often focus on infrastructure, costs, and scalability. Much less attention is paid to the structure of the electrolysis cell that underlines the technology. Whether it be membrane, electrode, or a catalyst, every component influences the entire system. I'm an optimist, but can material science considerations really help us to optimize the electrolysis stack? Hello and welcome to our new episode of Minus 253 degrees Celsius, the monthly expert talk that gets to the point, to the boiling point of hydrogen. And today we want to take a look inside the PEM electrolysis cell, into the heart of the system, so to speak, where chemical reactions and material properties set the pace. I've invited Anna Bernroitner to join me. She's an electrochemistry expert at the Bosch site in Linz. Anna, it's great to have you here. Thanks for joining us.
Hi, Keith. Nice to be here.
I know electrolysis involves water, electricity, a cathode, an anode, and a membrane. But can you explain to me again, in simple terms, what happens during PEM electrolysis?
So first of all, the PEM in PEM electrolysis stands for proton exchange membrane. To explain it from a very high-level perspective, water is split into hydrogen and oxygen using electricity. The anode is where the water is decomposed, and the cathode is where the hydrogen gas is generated.
What other components are important for the PEM electrolysis?
If you look at the cell coming from the cathode side, the GDL comes first. The GDL stands for gas diffusion layer and is made out of a porous carbon material, which is necessary for hydrogen removal and electricity supply to the reaction site. The site of the reaction then is the CCM, the catalyst-coated membrane. This CCM is made out of an electrically insulating but proton-conducting polymer, which has been coated on both sides with catalyst layers. Next comes the PTL, the porous transport layer, which is metallic and is necessary for water, gas, and electron conduction. The water comes to the CCM via the PTL, and on the CCM it is split into protons, electrons, and oxygen at the anode. The electrons then migrate through the CCM and react to form hydrogen at the cathode, and the hydrogen is then discharged via the GDL. At its core, it's simply about managing the flow of water and gases on both sides of the CCM, while also ensuring that electrons are brought in or taken out as needed. However, these two processes are initially contradictory, because electron conduction is best achieved with a solid material, like a metal. Water and gas transport, however, is best achieved with a material that isn't actually there. That's why we have porous layers on both sides of the CCM, which strike a balance.
Did I understand you correctly then? Would you say that electrolysis is a material science challenge?
If you want to put it that way, yes. That's why it's so important to study and investigate the properties of the materials as precisely as possible. We conduct electrochemical operation tests in full-scale tests and in subscale tests, but model systems are also of interest to us. We can also conduct tensile and compression tests with the CCM. The knowledge gained from all of these tests can then be used in simulations, for example. The simulations in turn promote new insights, and in this way we continually generate more knowledge.
Don't you get lost in the tests, the measurements, and the models?
You can measure many things and thus define many values. But it's not just about accumulating as much data as possible. It's about filtering and defining which parameters are relevant for the entire systems. Overall, we don't want to generate data for the sake of data. We want to optimize the PEM electrolysis stack at its core.
Are there any examples of how this has been achieved already?
A good example is the compression of the CCM, because it affects the lifetime of the entire stack. The CCM is always compressed. If you compress it tighter, then the electrical contact between PTL, GDL and CCM is improved. This, however, increases the mechanical stress on the CCM, which can make aging more likely or hinder the flow of materials to and from the reaction sites. So we're looking for an optimum, which lies somewhere in between.
Would you say that material science studies aim to improve the lifetime of the electrolysis stacks?
We aim to understand the degradation processes so we can take steps to prevent them or at least slow them down. That means we artificially induce accelerated aging.
I've already spoken to your colleague Piotr from Tilburg about these deliberately induced aging tests. Can you explain to us exactly what happens to the membrane when we talk about aging?
The CCM can become thinner over time, for example. One reason for that can be mechanical stress, like during the compression. Another possibility is chemical membrane degradation, where the CCM loses some of the polymer molecules that make the membrane.
Okay, I assume chemical membrane degradation is also something we need to better understand. Are there tests for that too?
There are tests for that too. To do this, we deliberately contaminate the electrolysis cell with various ions. These ions can then react catalytically and degrade the membrane. Or they block the important sites within the polymer that are necessary for proton conduction, which both renders the CCM ineffective. Furthermore, the catalysts on the outside of the CCM can become ineffective over time, for instance through catalyst poisoning, in which the active sites are blocked and rendered ineffective.
Looking ahead, let's say, to the year 2050, what do you hope to have advanced with your current work in that future?
So, looking ahead to 2050, I believe that our field will see significant advancements, especially in the development of sustainable materials like PFAS-free CCMs. My focus is on enhancing the durability and efficiency of electrolysis systems, which are necessary for supporting a low-carbon society. I hope to help create hydrogen technologies that not only meet our energy demands, but also align with our environmental goals.
Anna, thank you very much for these insights. I'm really looking forward to continuing this path from the membrane to more and more megawatts. And thanks to everyone for joining us at minus 253 degrees Celsius. It's the monthly expert talk that gets to the point, to the boiling point of hydrogen. We'll see you next time.